So let's let's also deal with another important function, which is the moment generating function, right? So let's say you have a random variable x is a random variable. So moment generating function MGF is denoted as mx of t equal to expectation of e to the power tx, right? So this is actually characteristic of a random variable. So you have definite formulae for each random variable, right? So let's say I'm still on Gaussians. So for Gaussian random variables, so let's say x is a random variable Gaussian with mean mu and sigma. So then the moment generating function is e to the power, just a second. Yeah, e to the power. So then it is, so then I'm taking expectation of e to the power tx, which is over the random variable x. So you can do the computation, but you finally get the value as e to the power mu t plus half sigma square t square, right? So let's say you are given a you are told that there is, so now the question can be that let's say you have a random variable x. You're told x is a random variable and the moment generating function of x is e to the power, let's say t plus let's say how much t plus 2t square, let's say, right? Something like that. Okay. Or let's say somebody wrote it like t times 1 plus 2t, right? So you can immediately compare with this formula. You don't need any other knowledge. You know that this is the formula of a Gaussian. It looks like a Gaussian. So you can immediately put in the values here. You can see that it is 1 times t and this is 2 is half times 4, right? So sigma square is equal to 4 and mu is equal to 1. So this is a Gaussian. You can immediately compute that this sigma square equal to 4 means sigma equal to 2. So this is a Gaussian random variable 1, 2. Is that clear? And so this is kind of the back computation that you will do. And then let's say if you're asked the value of, if you're asked the value of, let's say something like, what is the probability that x is less or equal to 1, right? Now you know that this is a Gaussian random variable with mean 1, right? So it will look somewhat like, so it will again be symmetrical around the value 1. So you know that this integration, the complete integration is 1. So this integration has to be half. So probability of x less or equal to 1 will be nothing but fx of 1, that is half. So this is how you will solve this kind of a question. Is this clear? Like I'm just trying to highlight this kind of a function, moment generating function. And so you will hopefully have access to a table of such functions. Otherwise, it is useful to know, at least for Gaussian, that this is the formula. And if you see the formula, you can directly find the values and you can solve this kind of questions from basic fundamentals.
So you mean if f of x is, can I ask it out?
Yeah.
Yeah. So f of x is 1 is it's mostly like this. It will be like minus infinity to 1 with 1 by root of 2 pi e power. So if you solve it, it will come 1 by 2, right?
Yeah,
Okay.
but you don't need to solve it. It's almost it's unsolvable, like I think, because like how will you integrate this kind of a function? E to the power minus half x square. How will you solve this integration normally? You can try substitution, you can try n number of things. Ultimately, like you can solve this integration without knowing probability formula, but then you will need to go to complex analysis and those kind of things, which even I have forgotten. But yeah, like this, like you don't need to solve that integral if you can identify these kind of patterns. If you can just use basic conceptual understanding, you can solve. Okay.
Okay.
Yeah. Right. So what else? So this is kind of a quick overview. Another notion is of independence and correlation. So let's say we are told that x and y are independent, right? What is the value of rho x comma y? Like, sorry, what is the value of, let's say, covariance x comma y? Can somebody answer? So again, for just to remind, covariance x comma y is expectation of xy minus expectation of x, expectation of y, right? That is the formula, kind of. A special case of this is the variance, where x, if you take, let's say, x and y as the same random variable, you get something known as the variance of x, right? Which is expectation of x square minus expectation of x whole square. But you want to capture the dependence between two variables, so you will go to covariance. So if you're told x and y are independent, how can you compute this quantity? Any answer?
You mean computing covariance of x and y?
Yeah. X and y are independent. So what will be the value of covariance of x and y?
If x and y are independent, there is one. Is it 0? No.
Yes, you're right. It is 0. Because if x and y are independent, what means is that expectation of x and y will be xy will be expectation of x times expectation of y, right? You can kind of derive it because, yeah, this is a property of independence. So if you have xy and if the PDF of xy is, you can write it as fx of x times fy of y. You do dx dy, you do the integration, you can separate it out into two separate integrations, right? X fx of x dx times y fy of y dy. So I just kind of very quickly derived it. So this is expectation of x, this is expectation of y. You get this formula. So then both of these terms will cancel out and you will get 0. So then what we know is if x and y are independent, so the property of independence guarantees at least in one direction. Sorry. Independence implies uncorrelation. Does that make sense? Because I just proved it, right? So covariance is 0. It means that The correlation coefficient is also 0. That is nothing but covariance divided by sigma x sigma y. So if two variables are independent, they will be uncorrelated for sure. Is the other way true? I'll leave this for you to study or give me a counter example or something like that. But this way is true. So this is kind of a very quick proof of that property. So these two are like the notion of independence, correlation, and how they are related. This is a very
The other
important.
way, I think even if it is uncorrelated,
Yeah.
but it may not be independent also. Because is that
Yeah.
correct?
Yeah.
Maybe dependent also, but maybe uncorrelated.
Yeah. But just to satisfy yourself, you should try and read or find a counter example, right? Like
Okay.
you can try to find a variable, two variables that are uncorrelated and show that they are not independent,
Okay.
right? You can
Okay.
find such example. Right. Then, yeah, there are, I can, this kind of covers mostly, yeah, mostly like kind of examples that you can figure out. Another, you can do similar small problems, but this is not meant to be a probability course. So this is a queuing theory course where you will need all of these notions of, continuous random variables, discrete random variables, distribution functions, PDFs, distribution functions. So it is really good to brush up on probability. I'm pretty sure all of you have some background, but it is important that you brush up a bit before going into queuing theory. Okay, so let's go to queuing theory now. And so this is one problem that I was kind of solving, right? I'll just erase it for a bit. So I'll kind of switch the order a little bit. I'll first cover the last chapter in your week 1, which is on Laplace transforms, right? Laplace transforms. Okay. Mm-hmm. 1 second. Yeah. So let's say you are provided a Laplace transform. What is a Laplace transform? Again, it is probability division, but somebody. Yeah. So Laplace transform is nothing but, so let's say you have some, yeah, you have some function f of x, let's say, right? So the Laplace transform of this function, this is the notation, it is denoted as integral 0 to infinity f of x, or in common it is denoted as t. So it is f of t to the power minus st dt, right? E to the power minus st dt. So this is how, so these are all, this is also another form of the moment generating function, or so there are many similar quantities So S here can be a complex number, etc. So S can actually be some complex number. So let's say some kind of X plus IY kind of thing, some complex number. And then this becomes a little bit of complex algebra. But so the thing is, you will be provided, or you should know, Laplace transforms of certain kinds of variables, and that you will need a little bit for your queuing theory. So this is again a little bit of probability revision, but yeah, 1 second. So we'll be taking one example of the gamma random variable, the gamma function, right? So the gamma distribution. So just to revise, this is another popular distribution where, so you have, it's denoted as, so f of x equal to beta to the power alpha on gamma alpha x to the power alpha minus 1 e to the power minus beta x greater than 0, right? So this is the notation of the gamma distribution with parameters alpha, comma, beta. This is the notation, right? So the Laplace transform for the gamma distribution is so the Laplace transform is, you can kind of look it up, it's beta to the power alpha. So if you put in f of x here, I mean dx doesn't matter, it's the same, then it will be dx. So if you plug it here and compute this value, you will get something like beta to the power alpha. So I'll write the proper notation, L of s for a gamma distribution equal to beta to the power beta by s plus beta to the power alpha, right? So just look at this formula and look at this. You are provided some Laplace transform which is of this form. So you might be provided something like this on the right hand side, right? Something like this, and you have to do the reverse factorization. Like I kind of made up a problem right now. So just go the other way, and you will have some function like this, which you can kind of factorize and get the actual form, which is the product of, so again, if you put alpha equal to 1, then the gamma reduces to an exponential with mean beta, right? Alpha equal to 1, then this becomes exponential with mean beta. So this is the Laplace transform of an exponential. This is to the power 1. So if you compare here beta by s plus beta to the power alpha. So here it's 2 by s plus 2 to the power 1. So alpha is 1, right? And then we'll have alpha is 1 and beta is 2. So this is exponential of 2. And this other one is gamma of 1, 2, right? So you have, it is kind of like the factor of like 2. So then again, since the Laplace transforms are independent, which means we have 2 independent random variables. Let's say x has a distribution of gamma 1, 2, and y has a distribution of exponential 2. So this is the Laplace transform of some random variable x. And you are asked to find the variance of x. So all of this math of Laplace transform, essentially, or it's also known as Laplace Stieltjes transform. It's kind of he's another scientist. So LS transform. So this is also there in your course. So you have to compute variance of x for this kind of a function. So now, actually here I shouldn't be conflicting notations. Let's say x is so then x is composed of x1 and x2, right? So I have two random variables, x1 and x2, which is exponential of 2. And so x is nothing but x1 times x2. And so variance, so x is x1 times x2, where x1 and x2 have these distributions. So variance of x will be variance of x1. Sorry, x is 1 plus x2 actually. So that is why when you have a sum of random variables, then your Laplace transform will become product, because you will do expectation of e to the power minus t x1 plus x2. That will give you e to the power minus s t1 plus t2, whatever. So it will give you expectation of e to the power minus sx1 times e to the power minus sx2. So all of this math, all of this factorization just tells you that, okay, I have two independent random variables that are being added up here. And so the variance will also be the sum, because these are independent. So you can kind of eliminate the dependent term here. So the variance will be sum of variance x1 and variance x2, right? And x1 is, again, gamma random variable with these parameters alpha, beta, mean and scale as 1 and 2. And so you can, these things, it's pretty much available online. You can always look up. And so you can find that for a gamma random variable, the variance is, just pull up the formula. So this is just calculation at this point, right? The variance is alpha by beta square. So like I'll just kind of note down the formula here, equal to alpha by beta square. So then this will be gamma 1 comma 2, that will be 1 by 4, 1 by 2 square, plus again alpha by beta square. So right, so this will be 2. This will be just again 1 by yeah, 1 alpha by beta square 2. I think. Yeah, I think I'm right. Anyway, this is just computation at this one, so you can just check, double check this. But the key trick here is to see this function, do the factorization correctly, identify what random variables are there, and then apply, and then realize that these are independent, and you can then express, you can use the properties of independence, which is express them as the sum of random variables and all that. Okay. You can just kind of fill in the details. I might not be correct. I might have made some calculation error. But yeah. So is this kind of clear? Like this Laplace transform math? Okay.
Yeah, Datta, actually, I just I didn't have time, so I just started to review from Markov chains and stochastic process. So
Yeah,
I
yeah, yeah.
really
No
couldn't.
worries.
Yeah.
Yeah, no worries. You can review it later. I just wanted to cover this first because this part is related to, more related to probability, and like it kind of just follows up rather than yeah, it's not, it's less related to other things. So for Markov chains, so let us now,
Also, I have
yeah,
some one query. See, actually, we have first assignment on 8th and second assignment is also on 8th actually.
okay.
So we had actually like first assignment we had some time. Since second assignment is less time, is it possible just to increase it for to some more days? So
So let me be very clear here. Let me be very clear. I am not responsible in any way with the NPTEL course administration. So I thought I'll discuss it later. But so I'm not responsible in any way with the NPTEL course administration. Those kinds of queries, you will have to ask the the administrators. So there must be an email ID provided. My role as a so I am a PMRF fellow, and my role here is just to clear doubts and help you with the assignments and the course content. And so that I'll try my best. I am just trying to solve some initial problems, and then any other queries on the course, that is on the content of the course that you have, I can try my level best to address.
sure.
Uh, on top of that, like these administrative issues, I am really not handling. Um, and for the record, for this work, I am not even required to talk to the course instructor. I haven't yet spoken to him. This is completely independent. I I happen to kind of be familiar with the course material, which is why this is kind of my duty to uh, help the NPTEL process. But I am not in any way interacting with the course instructor actually. I'm not even in IIT Guwahati, I'm in IIT Kanpur. So I really don't have any control, or I cannot help you in anything related to that aspect, course administration. As far as I think week 0 was just probability refresher, and so that is a kind of a prerequisite. So it is best for you, and also week 1 it was covered in the previous week. This week is already week 2.
Yeah.
So which I will again, this is how it will happen. I will cover, like, you should of course start studying on your own and try the assignment problems, and I'll do a session like this every week, same time, same Zoom link, and I'll help you in grasping the concepts and clear your doubts, all of that. And then, yeah, hopefully, if you are still stuck with some assignment problems, you can solve them on your own. This is the only time commitment that I have, these 2 hours every week. And yeah, so I can, this is the only time that I have available. Other queries regarding course administration, I am not the right person actually. This goes for both Sangeet and Mukesh, I think 2 students. Okay, great. So this was the more mathematical part, and the reason we are doing all of this math is to model queues, right? So this is like queues, as we know, and you will also see in the lecture, professor has explained in great detail that queues are these correct mathematical ways to model all of the phenomena that we see around us, right? Like you can go for grocery shopping, you will see a queue. In airports, like in airports, you'll see queues uh, in warehouses uh, and so in real life, everywhere you see queues, and also it is a very useful model for more abstract things. For example, it is used in supply chain management. It is used in computer architecture to model CPU, like instructions coming to and through the CPU. And particularly my specialization is in networks, computer and wireless networks. So it is used extensively in computer and wireless networks to model various processes, especially packet flows and also like but that processes regarding like cellular connections and all that. It is a very general mathematical course that you will do, which has enormous applications in various fields. So that is